Okay, so as some of you may have noticed, the board is not filled out, so I thought, well, next best thing we can do. All right, so here we have this opportunity to see what it is that we're working on. Okay, tomorrow, okay, you have your vocabulary evaluation to work on or complete tomorrow. We'll go over this problem, and then I'll hand those papers out. Okay, then we'll talk about horsepower on Wednesday and Thursday, and then depending upon that of the weather, we would like to be able to go outside and go onto the football field and then be able to test and or calculate how much horsepower you are generating. That's why it says horsepower activity here. So not a whole lot going on this week. We have one or two good distractions to continue to work forward as this week progresses. So keep in mind we still have a job to do regardless of what happens this week. All right. Any questions over what we're doing this week? Okay. Hand out a paper today. We'll go over this problem. You have this evaluation tomorrow. And then we'll start talking about horsepower on Wednesday and Thursday. Then we'll try to complete that activity on Friday. And if it would appear that the weather is not going to cooperate, perhaps we'll move it up a day or push it off till next week. Okay? Any questions over that? If not, we will go ahead and proceed. Nothing? Okay, and that's fine. So we can shut this off then? All right. Okay. A couple of things I would like to go over, though, before we hand this paper out. Okay? So what might be something that changes the direction of an applied force? It's part of your vocabulary. What might do that? Changes the direction of an applied force. And if one of the things we don't know, you certainly can open up that page of vocabulary of the definitions that you do have wrote and or written down. Nope, it's not quite that. Something that changes the direction of an applied force. Okay, that's what another student had said, but that has something to do with it. But no, it's not the definition of that. It might be something that we could use to increase the applied force. The example that we did is we had said maybe you have a flat tire. Yeah, it's a machine that would do that. So if you change the direction of applied force with a lever, we said you have the force going down, but the applied force is going up. So you're changing that direction. So that's what a machine would do. Okay? So what happens if we have an applied force that's over a certain distance? In other words, what happens when you multiply force times distance? What do you get? Yeah, you get work. And what's that work labeled in? Yeah, it's labeled in joules. So then, what might be a simple machine? We said this is a simple machine, but it's specifically called a what? Because it's got a fulcrum on it. It's a lever. That's right. So a lever is a simple machine. Okay? That's on a fixed point or a fulcrum. Okay? So what might be a simple machine that you might use a rope or chain with because it's got grooves around it? It's a circular machine with this that has grooves on it. Yeah, pulley. Yeah, exactly. You use a pulley for that. Well, what would the force applied to a machine maybe be? Is that output work or input work? Think of that again. The force applied to a machine. Is that going in or out? Say that again. That is an input force because what you get going out is your output force. That's the work done by the machine. Not on the machine, but by the machine. Okay. So one of the things we said in class, you have sickles in front of this that cut soybeans. Then that's going to go through this machine, and it's going to have, I think they're called sieves, that break the soybeans apart. When you have two simple machines that work together, it's no longer a simple machine, but rather a what? Perhaps. And it's probably one of your vocab terms. We're going over these for your benefit, and if you choose, we can keep going or we can discuss this problem. Discuss the problem. Asking for input. Okay. All right, so we'll go ahead and work over this problem in just a moment here. All right. One of the aspects that could get to be a little tricky is that if we have something that's labeled in a mass per meter per second squared, what does that resemble to you? If something is measured in a mass and you take it times acceleration, what are we measuring? Not quite momentum. That's got velocity in it, not acceleration. Yeah, you would be measuring a force. So what we mean by that is a force is a mass per acceleration, okay? And if we have a Newton per meter, in other words, what happens if you take newtons times meters? Because what is newtons measuring? Newtons is measuring force. And if you take that force times a distance, what are you calculating? You're calculating work. And a Newton per meter, okay, you multiply these two, you would possibly get what? You get work, but how do we measure work? Someone said it, even with my decreased amount of hearing, it was quiet enough. Yeah, it's measured in joules. Okay? So the reason we want to bring something like that up is what happens if we have a Newton over a centimeter or a meter squared. In other words, you have force divided by that. Force over that A is measuring what, and we have talked about it just very briefly. If you divide force by area. Because I think to jar your memory, we talked about CPR, cardiac pulmonary resuscitation. You're applying this on someone's chest. Pressure. So, in other words, a force per unit area is a pressure. And how do we measure pressure? In what? We just call it PC, pascals. So a force per unit area is pascals. All right. Because one of the things, you might see variables labeled like this or something like that. Okay? One of the things, we want to challenge your brain and try to meet those expectations, because we're all smart enough to do this, and nothing's going to be easy. If everything was easy, gosh, we'd all be doctors, lawyers, and certainly we'd all be farmers. Farming is definitely not easy. Okay? Some people think, yeah, just break the ground open, throw a seed in there, put a little water on there, and maybe do a little dance around it, and maybe you get a good crop. Is that what you farmers might do? You maybe dance out in the field? No? Okay. You out there with your equine, horsing around? Because what are equine? Horses. So you're out equining around? Maybe. Or else we'll just say quit equining around. Yeah. I think that's our age, Ms. Anderson. It's, oh. Okay. Do you ever think that, do you ever wish that all I ever want to be is happy all the time? Is that physiologically, is it possible? It's not even possible to do that, okay? And the reason for that is if we were happy all the time, it would decrease the amount of dopamine in our system. That has nothing to do with this now. In other words, let's see here. Who can we pick on in here? Okay? We like sugar, right? Okay? So we've got a Pop-Tart, which is fine. We have snacks in here. I don't make things an issue unless it becomes one. But why that Pop-Tart? Is it your favorite? Yep. You're just saying that.
No, it's my favorite.
Okay. So whether it's a Pop-Tart or whether it's, women are guilty of this. Women are always like chocolate, right? Who? No? No? I think there's a hole in the physics world here, Ms. Anderson. Women don't like chocolate, but you can't speak for all women. Don't take that the wrong way. Who does like chocolate in here? Oh, yeah, now raise your hand. Okay. One of the things that we like about chocolate is it gives you a reward. Your brain is sensing a reward because it likes the way that chocolate tastes. Okay? But what do you think it would be like if all you did was eat chocolate bars all day long? For one thing, you wouldn't feel very good. But two, eventually it's going to decrease that reward in your brain called dopamine. That dopamine says, oh man, we got my favorite chocolate bar. Oh, this chocolate bar is good. We got our favorite Pop-Tart. We really enjoy this Pop-Tart. But what happens is if you keep doing that over and over and over again, it takes away from, again, that reward. If we were always happy, always, it would take away from the dopamine release from being happy all the time. Everyone probably has different types of struggles to go through. And with that, hopefully we teach you those skills, because maybe some of you aren't doing as well as what you would have hoped, but with hard work, that will pay off, okay? It's one of the things, please, trust us, whether it is Mr. Deitch, Ms. Doctor, myself, okay, Mrs. Hemrick. If you keep working hard, it will pay off. And I got to ask, is that beef jerky? Oh, okay. So, very good. All right. So, when you look at this, just please keep working hard and it will pay off. If you choose to do that hard work. Some people might choose not to. Okay. So, moving forward, you've read the problem. What is the next thing you should do? So what do we know in this problem? Okay? Okay, so one at a time. I'm not that fast or smart. What's our mass? 1,700 kilograms. What else do we know? What else do we know? Okay. Whoever said initial velocity is right, but why are you right? You need to do that too, okay? But how do we know, how did you know that this was not a final velocity? Because something is happening later. It hasn't happened yet, okay? So keep that in mind, okay? So if this is the speed it was and it says something happened later, whatever that later is going to be your final velocity. Okay, so regardless, your initial velocity equals 65 meters per second, not squared because that's an acceleration. Okay, what else do we know in this problem?
Time.
Okay, what does your time equal?
0.12.
Do we know anything else?
Momentum.
Okay, we know our momentum. And a lot of you picking these variables, you are correct, but why are you right? It's one thing to say, well, we know the momentum, but why do you know you're right?
The label.
Because of your label. Okay, so what is the label for, or what is our variable for momentum? Okay, I'm willing to bet that's not all that we know, other than science is great. We know that too. Okay, keep going. Okay, so how many of you, well, let me use a different color just because that's what we have wrote/written down there. So let's go ahead and use this one. How many of you maybe did that?
Me.
Okay, so why might be a good idea to put something over this A? Because you need to find your acceleration. Okay, so what's our area?
0.80.
Now, one of the things that we said when it comes to area, if it's in meters squared, leave it in meters squared. If it's in centimeters squared, leave it in centimeters squared. For those of you taking physics years down the road, there might be some aspects you may need to work out, but we are giving you the tools at our level here. Whatever your area is labeled in, leave it in that. Okay, have we accounted for everything in here? We've got 1, 2, 3, 4. And time is 5. That should be all of them. Okay, now, what is the question ultimately asking? Okay, so once you see that, we want you to ask yourself, what do we need to know to solve for pressure? So why might you put maybe a line like that over top or a zigzag line?
You don't get it confused with momentum.
Yeah, so you don't get it confused with momentum. Okay, so pressure equals what over what?
Force over area.
Okay, so this is what we're ultimately looking for. Well, so we need a force and we know an area. So here we look at all this information. Well, we've got half of what we need, okay? We're not too far removed from you ding-dongs running down the hall like that too, are we? Oh, we're not ding-dongs, are we? Oh. You know, this is anatomically correct. You have a masseter muscle, okay? You've got a buccinator muscle, a zygomaticus muscle. Those muscles can flex, and when they flex, it causes you to smile. And if you smile, you will not break your face. Your face cannot break from flexing your muscles here. No, not from flexing muscles like that. They're just not big enough to cause a type of break. It has to be from some sort of outside force like that. that you can break your face. Okay? So, what do we need to know to solve for force? So in other words, we need this variable because we don't know. And someone said we need to know our acceleration. We don't know that either. Okay? So then finally, if we are looking for our pressure, that's also an unknown. So with everything that we have here, we're not going to solve for that first because we just don't have enough information. So what might we do to proceed further? And that's correct. Do we have enough information to solve for our acceleration? If we had our final velocity, we could. You need to find your final velocity. So how are you going to find your final velocity with all of this garbage here? Your momentum formula, okay? Because we know that our momentum, which is 120700, okay, equals our mass, which we said was 1,700 kilograms, times our final velocity. Now just think of how much personal growth a lot of you have accomplished since August, okay? And it's not going to be at the same rate, okay? So other people will learn at different rates. As we said, just trust us. If you keep working hard, good things will probably happen. So how do we get this final velocity all by itself? So what do we get for our final velocity?
71.
71?
Yeah.
Okay. So once we found our final velocity now, we can do this variable. What are we going to subtract from 71?
65.
So there's our final velocity. Well, that's what we did. Oh, okay. That's not the right number. Okay. 120700 divided by 1,700. That gives you 71.
It's not going to end back yet. We're not talking.
Oh, okay. I'm just not that important, and that's fine. We're just not that important in this case. Okay. So 71 minus what? 65 is going to be all over what? 0.12. So what is our acceleration now? 50? I believe you. Okay. So our acceleration then equals 50 meters per second squared. So now that we have this, okay, if we have an acceleration and we have a mass, what can we solve for? We're a bunch. Who's Star Wars in here besides me? May the Force be with you. With their lightsabers and the Jedi versus the Sith. Got their lightsabers here. No Star Wars people in here? Yeah, so I would say, may the force be with you. In this case, it's a force measured in newtons. Okay, so what is our force? We got to take 50 times what? $50 times 1,700, and what does that give you? A lot, I'm sure.
85000.
Okay, so we can erase some of this because we've solved for it. Okay, so we had said that force equals 8500. Is there anything after that?
0.
One more. Is that it? Forces are measured in what? Newtons. Okay, now we're on the home stretch. We've got the area, we've got the force. Now we can solve for this pressure. So what goes on the bottom part of our fraction? 0.80. And what goes on the top? Our force that we just calculated. 3 zeros, that's right. So our pressure finally is what? Okay, 10625? 250. And what do we measure pressure in? Pascals. You can do PC, you can do PA, maybe PA maybe makes more sense because for those of you who take chemistry in 2 years, you measure pressure in pascals, you measure pressure in kilopascals. That's important, especially when you start talking about the gas laws. Okay, questions over this problem? No? So then we'll turn you loose with this paper that we'll hand out, and we'll say, may the force be with you. Right? All right. So we'll catch up to you next time.